Thanks for coming. I'm Jung-Won from Kaisten IBS, and today I will talk about a polynomial kernel for sleep power deletion problem. This is a joint work with Edward Ivan in Royal Holloway, University of London, Oh Jung-Won in International University, and Sang In in IBS and KAIST. Let me first start with the definition of sleep powers. In 2002, Nishimura and Tlikos introduced this definition. For non-negative integer L, we say that G is an elliptic power over 3T if its vertex set is equal to the set of leaves of T, and two vertices X and Y are adjacent in G if and only if the distance between them in T is at most L. In this figure, the right graph is a triple power of the left tree. Here, these two leaves are of distance 2, so they are adjacent in this graph. And here, these three leaves are of distance 2 to each other, so they form a clique of size 3 in the right graph. Similarly, the right graph is a sleep power of the left tree. Here, these two leaves are of distance 3, so they are adjacent in this right graph. The motivation to study this graph class is originally came from computational biology. One main goal of computational biology is to find a phylogenetic tree. So what is a phylogenetic tree? It is a rooted tree where leaves correspond to species, and if two leaves are close to each other, then it means that they are similar in a sense of species. Given a graph G whose vertex set is a set of species, and edges represent some similarity among species, some biologists may ask whether we can extract some phylogenetic tree for G. In graph theoretical sense, we can formulate this question in terms of elliptic powers. So if we interpret this similarity in terms of the distance in a phylogenetic tree T, then we can formulate the previous question as follows. Can we find a tree T such that G is an elliptic power of T for fixed L? This is the main motivation to study elliptic powers in computational biology. In structural graph theory, sleep powers were already studied in many literatures. So in 2006, Dometal showed that a graph G is a sleep power if and only if it is coda and Boole-Dot-Gem-free, means that it has no induced subgraph isomorphic to one of graphs in the figure. So here, this graph is a Boole, and it is called a dart, and it is called a gem. Another characterization by Brandstad and Liu in 2006 is that a graph G is a sleep power if and only if G is obtained from a tree or a forest T by replacing each node with a clique of arbitrary size. Moreover, they show that sleep powers can be recognized in linear time. We call each replaced clique a bag, and a pair T, B, where B is the set of bags, is called the three-clique decomposition of G. In this figure, the left graph is a sleep powers, and so it has the three-clique decomposition. So I circled each bag, and the right graph is exactly that T. And one can easily check that the left graph can be obtained from this tree by replacing each node with a clique of arbitrary size. For instance, this node is replaced with a clique of size 2, and this node is replaced by a clique of size 3. There is also some motivation to study elliptic powers from computer science. So before to introduce it, let me first check some definitions related to complexity. A problem parameterized by K is fixed parameter tractable, or FPT, if it admits an algorithm of running time Fk times n to the C for input size n, constant C, and some computable function f. A decidable parameterized problem pi is said to be admitting a kernel if it admits a polynomial time preprocessing algorithm that, given an instance I, k, returns an equivalent instance whose size is bounded above by a function of k. If G is a polynomial, then we say that it admits a polynomial kernel. Let's see motivation from computer science. We focus on the following problem. Elliptic power deletion parameterized by the solution size k gets inputs as a graph G and a negative integer k, and it asks whether there is a vertex set S of size at most k such that G delete S is an elliptic power. For small l, these problems were already studied in computer science with different names. So when L is 0, then zero-leaf powers are exactly edgeless graphs. So this means that zero-leaf power deletion is equivalent to vertex cover. And when L is 1, a graph is one-leaf power if and only if it is isomorphic K2 or it has no edges. That is, one-leaf power deletion can be easily reduced to vertex cover. When L is 2, two-leaf powers are exactly cluster graphs, that is, disjoint union of cliques. So two-leaf power deletion is equivalent to cluster vertex deletion problem. So one can regard elliptic power deletion problem as a generalization of vertex cover and cluster deletion. This table surveys some known results on elliptic power deletion. And here, kernels only consider the number of vertices. When L is 0 or 1, then elliptic power deletion problem is equivalent to vertex cover or can be reduced to vertex cover. Recently, Chen et al. Gave the best FPT algorithm to solve vertex cover, and Memphis, Lochstanov et al. Independently present linear kernels for vertex cover. When L is 2, this problem is equivalent to cluster deletion, and Hupon et al. Present an FPT algorithm to solve it. And Bomin et al. Present a subquadratic kernel for cluster deletion problem, but the existence of linear kernel is still open. Dom et al. Show that sleep power deletion problem is FPT, but the existence of polynomial kernels was open before our result. So, and Alice Pool, Lautenbach suggests a structure for polynomial powers, which can be expressed by MSO logic, and Gursky and Wankel show that for every L, elliptic powers are over bounded clique width. So by Kuzet's method theorem, we can show that this problem is in FPT, but the existence of a polynomial kernel is still open. When L is a list of phi, since there is no structured theorem for elliptic powers, we don't know yet whether this problem is in FPT or not, and we also don't know that whether it admits a polynomial kernel. And our main result is that is to show that the power deletion problem admits a polynomial kernel. In the remaining of this talk, I will briefly explain our main ideas of our result. So these are main steps for a polynomial kernel. We say that set S is a vertex set S is a good modulator of G if for every vertex V in S, G delete S minus V is the Smith power. In our paper, we present a constant approximation algorithm for Smith power deletion problem, and based on this algorithm, we can find in polynomial time a good modulator S of G with big of k-square vertices. Since the size of S is already in polynomial of k, it suffices to reduce the size of G delete S. So to do this, we first reduce the number of components of G delete S in two subsets. That is, we first reduce the number of logic components. Here, logic means that containing at least two vertices. And then we reduce the number of isolated vertices. Afterward, we reduce the size of each component of G delete S. In this talk, I will explain how to reduce the number of logic components and the size of each non-clique component. Before to explain how to reduce the number, let me introduce our new concept of split. A complete split of a graph G is a vertex partition A, B such that each set has at least two vertices and the union of NA and NB is a clique. In this figure, you can see a graph looks like a fish, and I want to divide the vertex set of it into A, B, where A is the set of vertices in the left circle, and B is the remaining one. Here, red vertices are the vertices in the union of NA and NB, and they form a clique, so A, B is a complete split of this graph. Okay, then why complete splits are useful to derive a polynomial kernel? The reason is the following lemma. Let A, B be a complete split of G and H be an obstruction of G. If H is a whole, then H can only use the vertices in one side. And if H uses exactly two vertices in one side, then H is isomorphic to the blue. This lemma means that complete splits hold obstructions on one side, and it is very useful to show the safeness of the following marking procedure. Let's see this figure. Here is S, and these circles are components of G delete S. And for a component D of G delete S, if VD and the remaining vertices is not a complete split, then it means that D has a pair of two distinct neighbors in S, because of which it fails to be a complete split. So if, let's say, this component is D, and let's assume that this vertex set and the remaining one does not induce a complete split, then it means that we can always find some bad pair of vertices in S so that it blocks this component to induce a complete split. So for each pair of distinct vertices in S, we mark such the components which are blocked by this pair in some sense, in a sense, to not to form a complete split. And if after the marking procedure, if there is an unmarked component, then we can safely remove edges inside that component, which leads to reduce the number of logic components. Now let's jump to step 3. to reduce the size of each non-clique component. Again, let S be a co-modulator of G and C be a non-clique component of G delete S. Since S is a modulator, C is a 3 power, so it has a 3-clique decomposition T, B. And we can easily bound the size of each bag of C. So it suffices to bound the size of T. To do this, we designed 3 main rules. And the first one is used to reduce some redundant parts of T. Suppose that C has a bag B here, such that C delete B has a component D having no neighbors of S. Then we can remove most part of D except for the one bag in D which is connected to B. So this rule helps us to reduce the number of leaves of T. And this is the next rule. It looks quite complicated, but the philosophy behind this rule is very simple. Suppose that C has a bag B here, and such that C delete B has at least K plus 4 components, say D1 to Dk plus 4, such that their neighborhoods are exactly the same and satisfy either one of these conditions. Then we can safely remove any one among D1 to Dk plus 4 from G. This rule helps us to bound the maximum degree of T. And the last rule helps us to reduce the number of degree 2 nodes of T. So suppose that C has a bag B1 to Bm, which form a path in T for m at least 6, such that the neighborhood of B2 is the union of B1 and B3, and the neighborhood of B3 is the union of B2 and B4, and so on. Let BL be the minimum size bag among B3 to Bm minus 2 here. Then we can remove BL from G and completely join BL minus 1 and BL plus 1, so that we can reduce the number of degree 2 nodes of T. Let me recap these 3 rules. Remember that to reduce the size of C, since we can easily bound the size of each bag, it suffices to reduce the size of T. So rule 1 is used to reduce the number of leaves of T, and rule 2 is used to bound the maximum degree of T, and rule 3 is used to reduce the number of degree 2 nodes of T. Thus, we can reduce the size of C. And with all these processes, we can derive that 3 power deletion admits a polynomial kernel. Here are open problems. Remember that although 44 power deletion is FPT, the existence of a polynomial kernel is still open. And for L, which is at least 5, it is still open whether L power deletion is a FPT or not. About the recognition problem, for L from 4 to 6, it is known that there are polynomial time algorithms recognizing L powers. And for L, which is at least 7, Epstein and Harvey presents a linear time algorithm to recognize L powers for graphs of bounded degeneracy. But for general case, it is still open. Okay, this is the end of my talk, and thank you for your attention.